record. Yeah, absolutely. I have a mental block on this. And Ishida, you're gonna jump up because we bumped you yesterday. So yeah. Anyways, go ahead, Bennett.
So it's assignment 4, 1C and 1D, just kind of housekeeping stuff on alkenes with radicals.
Okay, let
Um,
me just open it up.
okay.
I can share the screen.
Okay.
Um, Assignment for answers. I'm just gonna make sure. I think I updated the answers because I think I had a mistake in them. Yeah, there we go. And find Zoom. Share screen. Okay. For 1D, sorry, which ones?
So for 1C, just first, was confused about why that didn't attack the double bond and make like two CLs as the product attaching. Um, like why that radical attacks that the hydrogen, the secondary hydrogen.
So if it attacks the double bond, the best radical you can get coming out of that would be a secondary radical.
Okay.
Do you agree?
Yes. Yes.
So if it attacks that hydrogen, the best radical we get is a secondary radical that's in resonance with the primary radical.
Yeah.
And resonance is better than isolation.
Okay.
So this is a more stable radical than attacking the
Okay.
double bond.
So then by that logic for D, then why wouldn't you attack the hydrogen that is on the phenol?
Because it's not in resonance with that. There's no hydrogen at this carbon here. You need a hydrogen at this carbon right here. Sorry, I'm trying to.
Oh, right.
And there's no hydrogen right there, so you don't have something similar. Does that help?
Okay. Yeah, yeah. So it's just because there is no hydrogen at all to.
There is no hydrogen alpha to the double bond to attack, so you can't get that kind of a Lilith radical.
Okay. And so is that still following the thing where it's attacking the weakest bond?
Yep, that's
Okay.
exactly what it's doing. You're making the most stable radical arises by cleaving the weakest bond.
Okay.
Like by definition, like unlike a positive and negative charge where you have to consider, okay, does the charge really want to be there? When you break a bond to make a positive or negative charge, it's not necessarily attacking the weakest bond. It's normally making the most stable charge. But radicals are literally you break the weakest bond because you are just breaking the chemical bond. You're not you're not adding instability because of charges. You are just breaking a chemical bond homolytically. And when you do that, you are breaking the weakest bond. And the weakest bond is always the bond that leads to the most stable radical.
Okay. So can you go up to C just quickly one more? Um, so it's the more stable product is it's because the alkene is in the middle rather than primary on the end.
Yeah, exactly.
Okay.
And that's why I've corrected this online. Yeah,
Okay.
because I had it
And
up.
then the last thing I have is the answer for 1D. Why is it not polymerization?
Ah, it is. I just didn't. I only drew one propagation step. It is polymerizing.
Okay.
That is a polymer. It is
Right.
adding
That's
to
what I
itself.
was. Yeah, I was
I just
thinking.
haven't kept. I only went one step. I didn't go multiple steps. It is a polymer.
And then termination, you would just add that phenyl radical cap and call it a
Yeah,
day.
well, what I did was I added two of the radical chains together, or two of the polymer chains together. But you could add another phenol radical. That would be acceptable. Yeah.
Okay. That's all.
Or you could disproportionate, as we just talked about with
Right.
the manual.
Right.
That would also be possible because there is a hydrogen on this carbon next to the
Yes.
radical, and so that could disproportionate. We make the double bond end. Yeah.
Okay. Thank you.
Yeah. So I want to catch up with the conversation that was going on in the chat along with that. Where the hell is the chat? There we go. Um, so when do you use the when do you use the resonance structure and propagation? You use the more stable form. So you're going to propagate not from the most stable radical. You're going to propagate from the most stable molecule. That's going to lead to the most stable molecule. So in if we were so if we go back up to C, having the radical at the secondary position here is more stable for the radical. But this is in resonance, right? This isn't like flipping back and forwards. These are existing at the same time. There are different ways of drawing the same thing. And this second one here is more stable once you make a bond here because it's going to be incorporated as a secondary double bond. So it's leading to a more stable product. Yeah, okay. And so that's why we're attacking the hydrogen next to the double bond, because we generate that more stable resonance stabilized radical instead of just a simple secondary radical. Okay, I think Ishida, you got kicked out last. We didn't get to you, so you're up next.
Okay, just give me 1 second. It says I can't share my screen.
Oh, that's because I'm sharing, so I'm just going to stop sharing. You should be able to share now.
Okay, for assignment 2, I was wondering why we can't put the carbocation here and do resonance and put the positive charge on the oxygen, because I thought that would be better.
So let's okay, really good question. Let's do you happen to have a tablet on you there? No. Okay, you know what? I'll annotate this. I'll annotate your screen. Don't move your screen at all.
Okay.
Okay. So let's say we do that.
Mhm.
Okay, so we have that, right?
Mhm.
I'm sorry for the just, you know, and then do resonance here. You're right that resonance is possible. I'm going to argue it's really shitty, and we'll talk about why. So you'd have this. Now let's just keep track of electrons. Okay. I'm just going to press over here so it moves my John Trant thing. Okay, so how many electrons are on the oxygen in the second resonance structure?
6.
Okay. What do you think about that?
See, I thought that wasn't good, but then I thought it would be better than having the positive on carbon. That's why I wasn't sure.
Okay, so how many electrons on carbon?
In this one,
Yeah,
like the
on the,
second
on
one,
the left.
oh, on the left, it would be 6.
Okay. So, do you prefer to have negative charges on oxygen or carbon?
I thought carbon had more priority for getting a full octet, so I thought oxygen, but I'm not sure.
Yeah, so oxygen prefers to have a negative charge,
Mm-hmm.
which means carbon prefers to have a positive charge.
Oh, because it's more electronegative?
It's more electropositive.
Like
Oxygen's more
yeah,
electronegative. Yeah.
yeah.
So, having a positive on carbon is bad. Having a positive on oxygen is horrible. Like abomination unto the Lord, kind of horrible kind of thing.
Mm-hmm.
It just doesn't
Okay.
happen. Now we draw a lot of oxygen positives, but that's because those oxygens have 8 electrons and they're positive, and
Mm-hmm.
that they have their full octet and they're positive. So they're not really positive; they're just formally positive. But this oxygen is really positive. This oxygen is missing electrons. It's 6 electrons,
Mm-hmm.
and that's much worse than C plus. Much
Okay.
worse. And when you think about how you really want to draw the resonance structure for a carbonyl, what you really want to do with every carbonyl is, well, you want to put the negative on oxygen, the positive on carbon. So what you want to do is that. That's how that double bond wants to break.
Mm-hmm.
And if we do that, now we have 2 positives next to each other, which is
Yeah.
really bad. So this is actually because that double bond is kind of like that. It already kind of always sort of polarized really strongly, and you have this good resonance with O
Mm-hmm.
minus C plus. That's why this double bond does not put the positive where we have it here, but it puts it where I have it in the answer.
Okay.
Because you basically, if you put the positive on that bottom carbon, you're putting it adjacent to another already positive carbon, and that's really, really bad.
Okay, that makes sense.
Cool.
And then I had a question from.
Yeah, so I'm giving it a try. I'll keep the chat window open.
From assignment 3, I didn't really understand this part. Like, why was this very unstable? Like, I wasn't exactly sure.
Sorry, I'm just gonna clear my annotations.
Yeah.
There we go. It's not so much that it's stupid unstable. It's just much less stable than the alternative.
Okay.
Like, because the alternative is to make sort of two double bonds that are in conjugation with one another. These ones aren't. Like those double bonds aren't, because those if you draw the p orbitals, they're actually on that middle carbon. They're perpendicular to each other, so those two double bonds are not in resonance with each other.
Mm-hmm.
And so it's not. It looks like it should have some sort of special stability because you got two double bonds next to each other. It should be really good. It's not. Those are called allenes. They don't really exist. They well, no, they do, but they're transient. Like that, you make them and they react almost instantaneously, like in a few nanoseconds. Because they there's a lot of electrons on that middle carbon, and it really, really, really does not want to be making two double bonds.
Okay. And then I had one last question.
Yeah. You're asking a really good question, and I don't like my answer I just gave you to that, so I need to think about that because I want to give a better answer. I just have not thought about allenes very much. Okay, yeah.
For this question, can we like attack the double bond instead of the H and do resonance? Because you didn't. I wasn't sure if there's like specific reasons. Like when should we like look at doing resonance?
So in the other examples, so this is basically a halogen attacking a double bond like this.
Mm-hmm.
And these guys really, really, really like attacking double bond directly and adding HBr across the double bond. When you're adding HBr like this, you don't really want to be making HBr again.
Mm-hmm.
It doesn't really want to do that. So this is much more selective for doing this kind of radical addition across double bond.
Like, is it because of like, is it HBr or is it
Yeah,
like the
HBr, HCl, HI, they tend
yeah?
to add across double bonds instead of doing that radical resonance thing. And
Okay.
I wish I had a better reason for it than carbon bromine bonds are quite strong. And since you're making that one first, it tends to want to make the carbon bromine bond instead of the bromine hydrogen bond.
Mm-hmm.
And I really do not like that answer, but it's the answer.
Okay, that makes
I
sense.
hate radicals.
That was all my questions. Thank you.
Yeah. Did anyone else not get to answer get their questions yesterday?
I was also kicked out
Okay,
yesterday.
then you're next.
Okay, so I just had like one question to go over and then a couple of logistical questions. So I was wondering if we could do an example for drawing a reaction coordinate diagram for SN1 with
Yeah, absolutely.
drawing the transition states.
Yeah, absolutely.
Because
So-
I still get a little bit confused with the transition states and also like determining if that's endothermic or exothermic. Because like, what if there is no charged species like as your nucleophile?
Yeah, so let's pick an example like I don't know, I'm just really big on ethanol right now.
Okay.
So let's say we have this.
I don't think you're sharing.
Oh, I am really not. Yeah,
Okay.
right. You know what? For shits and giggles, let's add some stuff. So this is clearly not an SN2 or E2. You don't have a strong base or strong nucleophile. You've got a
Right.
protic solvent. Ethanol is both the solvent and the only reagent. And you're adding heat, which tells you you're putting energy into the system. And normally that's not necessary for the SN2 or E2s.
Mm-hmm.
So we're making a carbocation. I think we could have a competition between E1 and SN1, but we're going to pretend it goes SN1. And if I ask this on a question, I'd say something like, give me the substitution product for this.
Okay.
Because this could do either. Or I would ask, give me both.
Right. Okay.
But, first thing to do is draw the mechanism. It goes flat, right?
Mm-hmm.
And then ethanol comes in. And then another equivalent of ethanol comes in to strip off that irritating extra hydrogen. Okay, so that's what we have. Now, let's say we draw the reaction coordinate diagram for this. So I'm just going to call these A, B, C, and D. A is a nice stable molecule. D is a slightly more stable molecule. B is a carbocation, so that's going to be very high in energy. C is an oxygen plus, it's going to be a little bit better than a carbocation. You need to have a little peak between each of them. Something like that.
Okay.
Okay. So overall, there's a transition state at every one of those maxima.
Right.
Okay. Overall, this reaction is exothermic. D is lower than A. But the transition from A to B is endothermic.
Mm-hmm.
That's fine. We're coupling it with two exothermic transitions from B to C and C to D. And so this can work. It doesn't necessarily have to go back to A.
Okay.
But so the overall reaction is exothermic, but this initial step is endothermic. And that's okay.
Right.
I think that's sort of something you were going at. Then let's take a look at the transition state.
It was the overall, like, why it would be exothermic. Is it because I minus is more stable than, say, like as a conjugate base than it is than like ETOH?
Well, what we've kind of gotten here is we're kind of generating HI on the other side.
Right.
And the carbon-iodine bond is quite weak, and the carbon-oxygen bond is quite strong.
Oh, okay.
So an oxygen-hydrogen bond, so what we're really trading is we're trading a carbon-iodine bond and an oxygen-hydrogen bond for a carbon-oxygen bond and a hydrogen-iodine bond. The hydrogen-iodine bond is pretty weak. The oxygen-hydrogen bond is pretty weak. The carbon-iodine bond is relatively weak. The carbon-oxygen bond is strong.
Oh, okay. Okay.
So when
Yeah,
you're
that
kind of
was what was
summing everything up
confusing me.
when you look at everything that's happening, that's why.
Okay. Yeah, because in a lot of the other ones there is like a leftover charged species, so it's easy to compare. But
Right. But there's always a chart. Nothing like I'm a little sloppy sometimes with saying what the counter ion is, but there's never like you can't have a charge in a bottle.
right, yeah, I know it's
Everything's
gonna
neutral in a bottle,
combine
so
with
there's always some sodium or something. Yeah.
Right.
Yeah, no, it's easier to compare. This one's harder. It's just you need to go, oh yeah, there's an H here. It's easy to forget that.
Okay.
So I think the transition state you're probably interested in is this one, right?
Yeah, pretty much.
Yeah. So it's the transition state of the rate determining step is probably the most important one. So what that is we're looking more by the Hammond postulate, we're closer in energy to B. So this transition state is going to look a lot more like B than it looks like A.
Okay.
Are you okay with me saying that?
Yes, yeah, that makes sense.
Okay. So you're going to have a big delta plus. It's not quite a full positive yet, but it's well on its way. We could write a big delta plus.
Hmm.
Big is relative. Let's write big. There we go. And so it's mostly delta plus, and that iodine is now well on its way to being gone, but it
Okay.
isn't gone yet. At this point, we haven't quite broken the carbon iodine bond yet.
Okay, and because we haven't yet, it's still, the transition state still doesn't have an overall charge.
No,
Okay,
because they're both in the transition state. Yeah.
right.
Yeah.
Okay, that makes sense.
Yeah. You're on your. So what the transition state is you're on the route between A and B, and we know we look more like B. B is a full carbocation, and we know all that happened was the iodine left, and so we need our transition state should be the iodine is leaving.
Right, yeah, that makes sense. It was just like figuring out the overall reaction, and then
No,
the
it's yeah.
partial and the partial charges always kind of like, I always get stuck there, but that makes sense.
We should actually probably still draw out. There's some the stereochemistry is starting to disintegrate. Like this is starting to flatten, but it's not flat yet. It's I don't know. We're probably approaching like flat, but we're not flat yet.
Okay, that makes sense.
Yeah, sort of.
Okay, and then I just had a couple of like logistical questions
Yeah.
for the exam.
Yeah.
For the like network type questions, the big ones putting everything together, is that going to be laid out the same way as it was like on the practice test?
I
Because
wouldn't see why not.
okay, in that case, would I be able to like take a screenshot of that and print it? Because when I've tried writing it out on my own, I somehow like if I'm not being extremely careful, I copy something down wrong and then I end up
So
messing
what
up
I will
everything.
do for those kind of questions is I'll have every single entry will be labeled with a letter.
Okay.
And so all you need to do is you could basically write a list with your entries.
Okay, that makes sense. Okay.
Yeah, no, because you could take a screenshot and copy it, but I also want to make it so that you could do that as well.
Okay, right. Because
Yeah.
I've been doing it and I just always make a mistake when I
No,
copy
it's
it
so
down.
easy. It's so easy. So what I'll probably do is, take a like label each of the boxes with a letter.
Okay, thank you. And then finally, I know you keep saying that carbonyl chemistry isn't on the isn't included except for the Grignards. Does carbonyl chemistry include oxidations and amide formation or no?
Yes.
Yes, it does. Okay, so that
And
won't
that's not
be
on there. Yeah.
okay.
It's not
So
evaluated on any of the assignments. I didn't give you practice questions on it, and so it's not fair for me to evaluate it on the exam.
okay, so in terms of that, I actually was wondering if I could share one of my reactions for my SciComm with you quickly, just for you to
Yeah.
check it because it is an amide
Yeah,
formation.
you're allowed to do amide. You can do anything you like on the SciComm.
Yeah, but I just wanted to make sure that it was right
Sure.
because we didn't really do it.
Yeah, sodium. So Victoria asked about sodium borohydride. Sodium borohydride reacting with carbonyls is not on the exam. Sodium borohydride is a nucleophile.
Okay, so can you see my screen?
Yeah.
I just wanted to check that this was
Perfect.
correctly done.
Absolutely perfect.
Okay, thank you so much.
Works.
For my break later, I'm baking this into some bread, so I didn't want to do this wrong. Okay, thank you so much.
Okay. Okay, I don't think anyone else was kicked out yesterday, or I think everyone was here. Megan, I know you were here yesterday, but I think you were Megan Bornay, but I think you were just chilling. Did you? I'm not sure I got to you.
Yeah, I just had a quick question. The ozonolysis problems still confuse me a little bit. So they had a few ozonolysis problems in assignment 2, and I was wondering if we could do one of those.
You know what? I've done quite a few of the ozonolysis problems. They're actually on the video that I did one yesterday.
Okay.
I'm going to pass doing that just because it is a little bit restricted on time. and they do take up quite a lot of time.
For
So-
sure. Then I just had one quick question
Yeah.
from assignment 1, just about it's similar to the question that we did earlier.
Okay.
I don't know if I can, it won't let me share my screen and I'm not sure why.
Okay. What? Can you give me the assignment question number?
Yeah, for sure. It is assignment 1H.
1H. Let me just pull it up. 1A, B, C, D, E, F, G. What the hell? Or 1AH or 1H? Assignment 1 or
1H.
assignment 1A?
1H. Like just assignment 1.
Okay, I am clearly a moron because I don't have answer key for that somewhere. There is no 1H on assignment 1. 1A has no H either. Are you assignment
9H.
9H?
Yeah.
9H, yes.
Okay, perfect.
Yeah, there's like, I don't think I numbered them, but there's mechanisms.
Yeah. It's that one then.
It's that 8. So what is the, I'm going to just share my screen and you're going to tell me which one we are doing. Share screen. I'm looking at the right screen, right?
Yes.
Okay.
Yeah, it's that very last one on the bottom right.
Okay. Bottom right.
Yeah.
This one. Okay.
Yeah,
Okay.
so
I'm
there
gonna
is
stop
the answer.
sharing and I'm going to do it. Because I have to share from my other computer. So that's the question, right?
Yeah.
Okay. Do you want to go through it, or do you have a specific question about it, or do you want me to go through it and you'll tell me where I'm losing you?
It's just the very first step where we're going to put the positive carbocation.
Yeah.
I originally thought it should go next to like NO2,
Mm-hmm.
but in the assignment answer key, it actually goes to the bottom there. And I was wondering if that had to do with resonance.
Everything has to do with resonance.
Yeah.
I've got a bit of a fetish. So the nitro group looks like that. You basically have a positive charge on nitrogen at all times in a nitro group. It's electron poor. It's basically donating 2 of its electrons away to one of the oxygens to make the double bond. And there's no other way to do it. Like the only other resonance structure you can draw for the poor nitro group is, really bad. No, I don't want Dropbox. Get away from me. Where you have double positive on a nitrogen, which is really, really awful. So poor nitrogen sticks with double bond oxygen. So what that means is putting a positive next to a positive is a bad idea.
Okay.
Because that nitrogen is already pulling a lot of electron density out of that carbon to neutralize itself, because it wants to grab electrons anywhere it can. So it's pulling electrons from everywhere. And it can't make another bond because it's already making 4 bonds. So it needs to pull electrons through the bonds. And so it's already making this carbon slightly positive. So you don't want to make it any more positive.
Okay, perfect. That makes sense. It was just I started to get confused when I started drawing the resonance, but that makes way more sense.
Now, if that nitrogen was just that, suddenly, yeah, now you have that lone pair and you can do resonance, and now you're definitely going to want to put the positive charge here.
Okay.
Yeah.
Okay, thank you.
You're welcome. I'm not sure who's next in line. I think I'm not gonna. So Swarty just asked. Okay, so there's an LDA question. Adriana, yes, absolutely. Um, Adriana says because nitro is an electron withdrawing, so it will destabilize positive charge on carbon. Yes, that is exactly why. Um, can I please do an LDA with an alkyne? Yeah, let's do that. So let's say we have this molecule, and I treat it with, I premix so what we're going to do is LDA is that. It's a very, very, very strong base. Alkynes are quite acidic. And so we're doing just a simple acid-base reaction. And this is where it's kind of weird that, yeah, you're going from N minus to C minus, and that seems like you're going the wrong way. But this negative charge is in sp orbital. This one is in sp3 orbital. And it's just really good to have that in sp orbital. It's really stable. So this is what we get from premixing these two. Now, C minus is a good nucleophile and it's a good base. I'd say it's an exceptional nucleophile because if you're thinking about is this stick like, it's like, holy shit, is it stick like? This is like 180 degrees to everything. There's nothing blocking this. Like if you're kind of build a model of this in Spartan or something, it kind of this negative charge sticks out like a sore thumb. It's just it's really sharp. It's a really sharp negative charge. And I've also stacked the deck because there's no way to eliminate because I have removed the hydrogen here. Even if I hadn't, it would still do an SN2. And so that's going to be able to do an SN2 on the iodide. It's a really good nucleophile. And that will give us note that I'm drawing the triple bond straight. This is all 180 degrees, so it needs to be straight. I can't do zigzagging with it because I will be wrong because it's 180 degrees on the end. That triple bond is like locks it in straight armed. And so that's what we would get. For this class, what we're going to see is the only thing I'd be using alkynes for. Normally they're used with carbonyls. We're not doing carbonyls. So the only thing we're going to be seeing alkynes for is nucleophilic attacks. And they can do acid-base reactions. So if, for example, this molecule had an OH on it, and I mix those things together, this would not attack the iodine. It would have gone and taken away the hydrogen because it's a really strong base. Which, of course, would then give us an O minus. And I would look and I go, okay, 1, 2, 3, 4, 5, 6. That's 6 atoms. And then the O minus would have come in and kicked out the iodine. That's because acid-base reactions are really super fast. So I've actually kind of broken the rules here, and I answered Suklin's question, but it seemed like a really, really relevant question. I want to talk about that. Sodium borohydride could do the same thing. It acts as a nucleophile, so for Victoria's question, and Victoria is actually next up. So I don't know if you have another question, Victoria, or if that was your question. You're muted, Victoria.
Yeah, I realized typing is much slower than talking.
Yeah.
So actually my question was specifically the bonus on the practice exam. And there was actually like so it's an alkane doing a radical reaction. But then there's also an alcohol group over there. And the way that I ended up doing it actually like when I did that question, or I'm not sure if you want me to share.
You know what? I'm going to stop sharing. Yeah, if you want to share. I can't remember what the bonus was.
If I can, hopefully. I've never done this before.
Oh, I've actually got it open here. So the bonus I see, I can share.
Yeah, go ahead. Yeah.
So this was the bonus,
No, not
right?
the bonus. The bonus on 43. So it's like the bottom two boxes.
Oh, the
Yeah.
bonus questions there. Yes.
So the way that I ended up interpreting it was I basically like looked at radical stability, like where it would be the most stable, and then I put it actually on the tertiary like center that's the farthest away from like the alcohol group.
Nope.
Okay, that's wrong. Okay, cool.
There's another more stable center. But you're thinking about this exactly right. You did the math wrong. There's a better center.
So where would it be next to the benzene?
As I said, I can't answer the questions on the exam.
Well, I know. I'm confused at like what the mental process, like we can do like a separate example, but
Resonance is generally better than tertiary centers.
I see. Okay. So okay, cool. Because I did see that on one of the assignments there was also actually I just had it, but this is the fault with printing everything out. I think it might have been on an assignment 4. I just saw it. Yeah. So assignment 4B, I saw that we did have an alkane over there. And then it was like Cl2.
Assignment 4B.
Yeah, assignment 4, like 1B.
Okay, I'm just gonna. I feel like I spent a lot of.
It's okay if not. Like I
need to stop this.
not a problem. You don't.
No, I just need to open it up. That's all.
Sorry.
I just feel like like we've been spending a lot of time talking about radicals, which is fine. It's the last thing in the course. It makes sense. That's why we're talking so much about it.
Yeah, I had a feeling too.
And they're hard. Yeah. So here, this is exactly what happened because the tertiary center is the only good site.
Yeah.
There's no resonance possible.
But if there is resonance possible, always go for the resonance.
Resonance is great.
Yeah, because in other examples, like I know that we weren't really touching the benzene ring because it's just like so nice the way that it is.
Yeah, so we're not going to be touching the benzene ring with that resonance. We're going to be working next to it.
I see. Okay.
Yeah.
Okay.
But we're not gonna break any of its double bonds, so we're not gonna react with its double bonds. Yeah.
Mm-hmm. Nobody wants to bother its double bonds.
No one wants to bother benzene's double bonds. Exactly.
Okay. So with this example, it would just land on the tertiary center because it's just the most stable that way.
Yeah, 4B you land on tertiary because that's all you got. Every other option is either secondary or primary. Those are all worse than having tertiary.
Mm-hmm. Okay. So it just comes down to stability.
Everything comes down to stability.
Fair enough. But if I could sum up the course in one word, everything comes down to stability.
Yes. Like that's not just the course, that's just chemistry. Like all of chemistry, everything comes down to stability.
That is true. Okay, thank you.
You're welcome. Rose.
Hello. Okay, I have a question about maybe I'll just share.
Yeah, I think I've stopped sharing. So yes, you should be able to.
There's no usually there's a screen to share. Maybe I'll just ask you to pull it up then. For assignment X, question. Why am I so confused? Okay, question 1F.
Yeah.
Okay. Now for the two of them that are said to be equal, I thought that I don't know. Is there induction in the first one that's marked as 2? I thought that would make it worse.
It probably is slightly worse. I'd accept equal.
Okay.
I can get really. This is a harder question I've asked. I've also missed a final resonance structure, which I think Keith pointed out to me last time, which is that final oxygen neuron. The final structure could make a double bond between the oxygen and nitrogen, which is basically a resonance structure of the first one and really, really good. It's basically the same thing as the first one. But having what I did there is basically I've got 2 carbons with 6 electrons. They both kind of suck.
Okay. And when you talk about like the triple bond thing, what is that like? Okay, yeah, I can't make a triple bond, but what is it referring to?
I think what someone What the hell am I referring to? I'm not sure. I think when I've gone through this before, somebody has tried to push the oxygen lone pair down towards the carbon to make a triple bond, but that would be really bad. It'll give you an O2 plus. Or if you try and donate the lone, what you can't do is you can't donate the lone pair from nitrogen directly to the nitrogen oxygen double bond without breaking the oxygen carbon double bond. But that's not a triple bond. I'm actually not sure what I'm referring to there.
Alrighty.
Yeah. It's true. It's a true statement, but I don't know what I'm referring to.
Okay, and then again for radicals, just for attacking the double bond versus the hydrogen, we did an example in class with like HBr and like benzoyl peroxide, and then we attacked we used like the double bond in propene to methyl. Oh, I said that backwards, but
Methyl propane. Yeah.
Is that so? You said something about if there's a halogen, we use double bond.
Yeah, we use double bond. You do the anti-Markovnikov addition of HBr or HI.
Okay, so that's when we use the double bond.
Right, and it's because the carbon-bromine bond is really, really strong.
Okay, and would that be the same case for like BR-BR?
That you can start getting a bit more of a mess. Chlorine, you do the allylic one, as we saw in one of those examples. BR-BR, you would add to the double bond, and it's because of small strength differences between bromine and chlorine. I'm going to try and avoid those kind of borderline cases because I don't really need you guys to memorize tables or look up tables of bond dissociation energies.
Okay.
Yeah, we just haven't spent a lot of time talking about it because it's stupid.
Okay.
Yeah.
So for polymerization to occur, do you have to attack or use a double bond?
Yeah, you do. Otherwise, it's not going to polymerize.
Okay. Okay. And then I just got a little confused because the book said something about radicals being sp3, but I remember you saying that the radical is in a p orbital.
It varies, and it depends on the radical. You can have either a triplet or a singlet radical. It can either be sp or p or sp3. It does depend on what it can do. If it can do resonance, it'll sit in a p orbital.
Oh, okay.
If it can't do resonance, it tends to sit in an sp orbital.
sp?
Or sp3, like one of these hybridized orbitals, depending on the hybridization of the rest of the atom.
Oh,
so yeah.
Okay.
So basically, if it can do resonance, it sits in a p orbital.
Okay.
And I think a lot of the time we've been discussing it, we've been able to do resonance. Yeah.
Okay. Okay, one more thing. If we have like there's a question like where does the equilibrium like lie? And like obviously we look at the charged molecules. But if the charges are positive, should we look at like the stability of the like carbocation?
Yes.
Okay, because I was confused if like we should like convert it like
you have to always look at it because charge gives you the instability. So it's whether it's positive or negative, you're taught the instability is what's driving the equilibrium one way or the other.
Right, because negative, like if you have a negative charge species, like in that sort of case, like likely it's the base, right?
Yeah.
But if it's positive, it's likely the acid.
Yeah.
So, but we're not gonna like flip things around so that we're looking at the base. We're gonna look at the acid since this is the one that's charged.
Yeah.
Okay.
Because what you want to do is you want to stabilize the charge.
Okay.
Whether it's a positive charge or a negative charge, you want to stabilize the charge.
Okay.
Yeah.
And just, I don't know if you can answer this without an example, but for like both radicals and carbocations, like I'm just a little confused. Sometimes we look at like the resonance that the molecule does before anything happens, and sometimes we look at like the the resonance that happens like after the reaction, like when there's the positive charge or radical? Like, is there a case for each of them?
So yeah, so I think for something like an SN1 or E1 reaction, what we're looking at is what we're interested in is the resonances available to the intermediate. So of the carbocation, because we're looking to stabilize that charge. If we're doing an SN2 type of thing, there was a Mobius question about this in the last assignment where we had an allylic iodide versus just a primary iodide, and the allylic iodide reacted faster, and it's because the carbon iodine bond is weaker because there's some delocalization from the double bond adjacent to it. So in that case, we're kind of looking at what kind of resonance is possible, sort of conceivable, before you do any reaction, because that's going to tell us a little bit about reactivity, even if there's no carbocation ever formed in SN2.
Okay, so what you're saying is E2SN2 is look at the resonance in the starting material.
Yeah, consider it. Yeah.
SN1E1 look at the resonance it can do once it's a carbocation.
Right, because that actually exists.
And that would be the same idea for radicals? Like,
yeah.
Okay.
Radicals were almost always interested in what the product is going to look like. Yeah. Like you need to make a radical. If you're making a radical in the first point, you want to know, are you making a stable radical? And then try to figure out how that radical reacts. You want to know, are you making a stable product? Because the radical is if the radical is in resonance, like if you have a radical and it can do resonance, then that radical it's not flipping back and forth between resonance structures. It is all of them at the same time. And so it's going to react to leave itself the most stable it can. So you're going to have your double bond disubstituted, for example, if you can.
Okay, that makes sense.
Yeah.
Thank you.
Because that transition state is going to be lower than one where it's monosubstituted.
Okay.
Hopefully me adding that last word there didn't just make it all much worse.
A
little bit, okay. Yeah. I'm going to move on because we're running out of time. So,
Great.
Casey.
Okay, thank you.
Do you have anything, Casey?
Yeah, I was just going to ask about assignment X, question 4C.
Okay. 3C, 4C down here. I'm not sharing my screen. Yeah.
I was just a little bit confused with the nitrogen with the positive charge on it.
Yeah.
And the acid base equilibrium.
Well, it can't give it sort of stabilizes that negative because of induction, but it can't give, it can't involve itself in resonance. You can't, because that nitrogen's already making 4 bonds, and those are all carbons. So you can't take off any hydrogens on it. So that nitrogen's stuck with a positive charge. So we're doing this acid-base reaction. We're taking out the most acidic proton on the other side. The resonance structure I haven't drawn, which might make a bit more sense of this, and I'm not sure why I didn't. I'm just going to annotate. Oops. No, I'm wrong. No, I'm no. Ugh. This is the resonance structure that really makes that left guy pretty stable, because we can put negative charge right next to the positive. They can't make a bond because nitrogen's already using all 4 of its orbitals, but you have a really good electrostatic attraction. Like that nitrogen can pull that negative charge through the carbon-nitrogen single bond towards.
So like the charges being really close together would be better than none of that at all then?
Yeah, because they kind of sort of cancel each other out. Like if they could make a bond, they would cancel each other out, right?
Yeah.
But they can't. But still, they're able to both modulate each other, right? Because think about that nitrogen carbon bond and where those electrons are going to be sitting in it. The carbon has too many electrons. Nitrogen doesn't have enough. The nitrogen is going to basically haul all the electrons in a nitrogen carbon bond towards it. So it's almost correct to do a resonance structure like this, where I basically break nitrogen carbon bond, and what you have is no sigma bond between them, but they're just kind of in close proximity.
Oh, I see. Okay. That makes sense.
And this would be a carbene. It would be a plus minus. We saw those. And so now there's no charges anywhere because these two cancel each other out because they're on the same atom.
Hmm.
And this is really quite good. And like this is an extreme that doesn't happen, but the nitrogen can almost steal all those electrons and neutralize itself. Just really, really polarize that bond.
Okay. And then I had another question. I just sent you that email this morning and I saw your response about that last question on assignment 4, I believe it was, with the mechanism for IBR.
Yeah, I got it backwards, and I'm going to upload the correction.
So, like, what reagent would you use then for that?
It's not possible with the chemistry we've seen.
Okay. Okay, thank you.
You'd have to walk around and like stick in some oxygens and then displace them in turn. I think it would be possible. You wouldn't be able to do it with a single reagent.
I see. Okay, thank you. That's all my question.
Okay, we're over 10 o'clock. I've got to run for another meeting because that is my life. So I'm going to stop sharing. And if any of you guys, I've tried to answer your questions so clean, but if any of the rest of you guys have other questions, I'll be back again tomorrow morning, same time. And then it's exam time. These are really good questions. I have no idea how the class is doing, but based on the questions I'm getting in office hours this year compared to the questions I've gotten in office hours in previous years, this is the group that are coming to office hours and asking questions are in good shape. Okay. Bye.